Well, thanks for being here today. It would have been weird to give my lecture to an empty room, but I would have done it somehow. I'm going to later after I do this, finish this proof, which is going to be kind of clean and easy, I hope. I'll go over the exam and answer any questions about it. But last time I got overboard describing the General Cauchy theorem and sort of giving examples and drawing pictures. Today I want to finish the proof I started. So remember what the theorem was. A cycle in a domain omega is basically a collection of closed curves. And in fact that is what it is, a collection of closed curves. And there's a general Cauchy theorem that says if f is analytic on omega and a gamma has a special property, namely being homologous to 0, that means when you add up the indices with respect to all those gammas for a point A, that should be 0 whenever A is in the complement of omega. That's a new definition. Then the Cauchy theorem holds in the sense that when you add up the integrals around all those closed contours of the function, you get 0 of an analytic function, and there's a Cauchy integral formula. The new thing about the Cauchy integral formula is that when A is not on any of the curves, then you have to multiply the value of f of A in the Cauchy integral formula by the index. So if you go around the curve twice, you expect it to double in the formula, etc. But it's sort of more topologically complicated than that. And the picture of the classic example of that homologous to 0 thing is a domain with holes. And if you have the interior holes, you put a curve going around clockwise. And the outer boundary, you have a curve going around counterclockwise. And that's the feeling for being homologous to 0. If I take a point outside omega in this picture, like here, of course it's a 0 out there, but even here it's 0 because the outer counterclockwise one, that index would be 1, and the inner clockwise one, that index would be -1, and the other one, that index is 0 with respect to that A in that hole. So they add up 1 minus 1 plus 0 is 0. Okay. Similarly for this one. Questions about that? Well, last time I started the proof, and I defined, so step 1, I defined G of ZW, kind of a sneaky thing to define. It's a difference quotient when Z is unequal to W. And it's equal to F prime when Z equals W. And last time I showed you in very elementary, so that was 0 basically. And step 1, I showed you last time that G is continuous. On omega cross omega, and it was very elementary, just kind of like the proof of the fundamental theorem of calculus. So that was last time. And today I'm going to show you that, I did that last time, and last time I also defined H. H of Z is what you get from integrating G in the W variable around the cycles. Okay. now I'm going to show you that H is analytic on omega. And in fact, we're going to show that H extends to be a entire function. And it's going to be a bounded entire function. So it's going to be constant. And that constant's going to be 0. And that's going to be basically the proof. So step 3 is to see that H is analytic. And this turns out to be sneaky and very simple without doing any analysis at all, hardly. It's going to be Morera's theorem. So show H is analytic on omega. It's going to extend to be analytic on the whole complex plane. Let's see. So first thing you got to do when you show that is that H is continuous on omega. So that's the easy thing, just to look at it kind of. Clear that H is continuous. I'm going to use Morera's, so that's a prerequisite. That's probably what Stein would say, but I'd like to say a few more words about that. Why? Let's see, how do you do things like this? Well, G, we know G is continuous on omega cross omega. And the trace of gamma, capital Gamma, is the union of the traces of the the curves that make it up. So that'd be the union of the traces of the gamma k's, however many there are, that's compact, because it's a finite union of compact sets, closed and bounded sets. And so G is continuous. Let's take a point, suppose Z naught is an omega. I want to show it's continuous at Z naught. Well, omega is open. So there exists a disk of radius rho about Z naught, closure contained in omega, with a positive rho. And now we have G is continuous on a compact set, on a compact D rho of Z naught, which is closed and bounded, cross the trace of gamma. And so it's uniformly continuous on that. And then using an estimate for uniform continuity, give me an epsilon bigger than 0, and using an estimate for uniform continuity on that product topology, the rest is easy. The rest sounds like let epsilon be bigger than 0 and use uniform continuity, ... Questions about that? That's just basic analysis.
Wouldn't we be able to, more simply show this just that h of, x plus, I want to say h again, but that doesn't quite work, but h of x plus some other constant is just going to be the maximum, or the total length of gamma times the difference between the continuous function, and then we can do it that way?
Well, you're integrating over a compact set, and so you got to make sure it's uniformly small on that compact set. And that's uniform continuity, basically. Once you have uniform continuity, then you're right. It just is. That's all there is to it.
Yes.
Well, now for the very clever thing is to use Morera's. B. Apply Morera's. Okay, so let's see. Suppose gamma is in omega, is a triangle. And then, since h is continuous, we know we can talk about the integral around a triangle h dz. And of course, that's the integral of, let's see, h is the integral around gamma of g of zw dw. And then we integrate dz. And if you write those out in terms of the definition, you get a sum of real integrals. And you've got the a and the b of the parameterization of the triangle, and then you'd have alphas and betas, j's of the parameterizations of the gammas. And when you look at those, they're real integrals. You take the real and imaginary parts, they're real integrals. And you can change the order of integration by Fubini's. So it's the most elementary version of Fubini's theorem on closed intervals and a continuous function on the underlying rectangles. So the most elementary form of Fubini's theorem. Nothing fancy, no measure theory, just continuous functions. So, you apply that Fubini theorem. And you change the order of integration, and you do an integral first with respect to gamma, and then an integral around the triangle of gzw. Let's see, this would be dz, and then the dw would go outside. And we know for a fixed w, the g has a removable singularity. So that's the key here. This one is easily, this is 0. G has a removable singularity. So this is equal to 0. Because G has a removable singularity at W, when W is fixed. Okay, that's really sneaky. Let's see, why is that? Remember, G of ZW is the difference quotient, f of z minus f of w over z minus w, and then it'd be f prime of w at w. Of course, it's continuous up to that spot, and therefore that singularity is removable. So Morera's implies that, so we get a big fat 0 here. And Morera's therefore implies that H is analytic. Questions? Well, let's see. I told you I would extend H to the outside of omega. And let's write. Let's see. So I'm going to draw that picture again. Maybe I should just copy it. Here it is. Let's make it bigger. Okay, so let's see. That's my shaded region there is omega. And think about what my h of z is going to be outside of omega. And so when I write down my h of z is equal to, let's have a z out here maybe. H of z is equal to the integral around gamma of f of z minus f of w over z minus w. Because z is not on the trace of gamma, so that so those could never be equal. Z is never equal to w. So that g thing in there would never be the f prime thing, because z is never equal to w. And let's say we're integrating dw. And when I write that out and pull it apart, I can pull, f of z is just a constant, so I can pull that out. I get an integral around gamma of 1 over z minus w dw, and then I would get minus the integral around gamma of f of w over z minus w dw. And that's in a place where the z, where that it's homologous to 0 out there. That gamma of index of gamma with respect to z would be 0 out there. It's definitely 0 out here. But if I, remember it's an analytic function on the complement. So if I slide into the bit inside a little bit, it's going to stay 0. So I would think of starting it out here and going in to that spot and see that, aha, that's going to be 0. So this is just motivation at the moment. This is equal to 0 outside gamma, when z is outside gamma. Not outside gamma, outside omega. That's what it means to be homologous to 0. And so we see what h should be outside. So the aha moment is, let's define, I'll call it h twiddle at the moment, because it's going to extend h. So h twiddle of z equals minus integral around gamma of f of w over z minus w. And it turns out you can define that on omega twiddle, which is equal to the z in the complex plane such, let's see, it's in the complex plane minus the trace of gamma, where the index is 0. In the picture, let's see, where would that be? Go back to the picture. I don't want to make a mess here. But everything out here would be a spot like that, where the index would be 0 out there. So it's going to include more than just the complement. It sneaks into the domain a little bit. Okay? I'll say more about that in a second.
Would it also be in the inside?
Yeah, in the inside holes too. So it would sneak out to those curves from the inside holes. Right. Well, let's see some simple facts. Easy facts. C minus this trace of this is a compact thing, so it's closed. So that's open. And consists of finitely many components. Let's just say that. And consists of connected components. It's a union of connected components. So I won't say consist. And we don't have to even think about it being finite, but in the pictures it's always finite. Is open and is a union of connected components. And since the index is constant on connected components, might be different constants. We see that omega twiddle is just a union of those open components. That's where it's 0. We see omega twiddle is a union of those open connected components. In the picture, it would be the outside, the unbounded component, and those two holes. So omega twiddle is open. Okay. So that's number 1. Number 2, open set omega union open set omega twiddle is C. Because of the definition of homologous to 0. Okay. That's a true thing. 3, H twiddle is analytic on omega twiddle. That's homework 2, problem 1. Homework 2, problem 1, that you can differentiate Cauchy integral formula, basically. And we've shown that H, the formula when I said the aha moment, was we saw that H was equal to H twiddle on the intersection. We saw that from the definition above when we said aha. So those are the biggies, and that means that that's how we extend H. So how do we define, What that shows is that H twiddle extends H. When you pick a point in the whole complex plane, if it's in the intersection, then it's clearly analytic on an open little disk, and if it's in omega but not the other one, it is clearly. So, and if it's in the complement, it is clearly. So there's 3 overlaps to think about, but we've shown it's analytic on all those 3 overlaps. So H twiddle extends H to C as an entire function. So we'll call it H. I'm not going to mess around with H twiddle anymore. Call the extension H. From now on. Questions so far? Okay, now I got to get a bounded entire. So my next step is to show that H goes to 0 at infinity. Okay, well, let's see. I'll draw a picture to see that. I wonder if I still have my domain. I do. Okay, there's my domain. Now I'm going to shrink it. There's my domain. And now let's see, I need to move it. I'm looking at it from outer space. I'll put a great big disk around it. Doesn't have to be centered like that. Let's make this be 0, and this be a gigantic radius r. If I'm out here, the index with respect to all those curves is clearly 0. Because we know on the unbounded components, the index of all those things are 0. So, in the picture like that, the index with respect to gamma of z is equal to 0 when z is outside a big disk. dr0.
I have a quick question.
Yeah.
So, does gamma need to be bounded, or is it unbounded, or can it be unbounded?
Gamma could be unbounded. But I'm talking now, when we talk about this, the index makes sense because the index is a compact set. I mean, gamma is a compact set. So this, the blue stuff might come out and be weird, but at least the gamma's in there.
Yeah,
So maybe I should erase the blue stuff and just leave the gamma, the curves.
Yeah, when I said unbounded, I meant omega.
Yeah, that's a good point, though. Yeah. Okay, so that's in the picture, and that means for h out for z, like in the picture there, we would have that. Let's see, h of z, by definition, would be. Remember, it was when the index was 0, a piece went away, and it was just this part of the integral. Okay. And let me see, I'll put a modulus here. And that's going to be less than or equal to, let's see, if you could generalize our basic estimate. This is really a sum of those integrals, but it's the max over gamma of f. Let's see, how close can my w in this picture is going around one of these curves. There's my w in the integral. And so the distance from z to w is certainly less than or equal to, let's see, so that I need to greater than or equal to in the bottom, in the denominator. And so this would be, let's see, the distance of mod z minus r. That's this little distance here. Mod z minus r. That's clearly less than the distance from that w to z, because w is inside that disk. So that being less than the denominator, that makes the quotient there bigger. And then finally, we need to multiply that whole thing by the length of gamma, which is the sum of the lengths of the curves. So you could define all these things. The length of the cycle would be the sum of the lengths of the closed curves. Anyway, it's the basic estimate, noting that w doesn't get anywhere near the z in the denominator, and bounding it by that. And that clearly goes to 0 as z goes to infinity. So we're basically done. So let's see, what am I? I'm done with something. I'm done with showing that 1 over 2 pi I integral of gamma of f of z minus f of w over z minus w. Remember that g would be the derivative when z is equal to w. So if I have z is not in the trace, then those would never be equal. So I'd never have the f prime in there. So we're done. And we know that's a big fat 0 now. That extends to be an entire function, and then that entire function was 0. So I should say here, so Liouville's implies that h is identically 0 on C. And now I write out what h is, and when I have a z not in the trace, that gives me that is 0. And so remember, when I pull out the f of z, I would get, so f of z times 1 over 2 pi I index around gamma of 1 over z minus w dw. That's the index, basically. Let's see. That's minus the index. I guess I should put it on there. Equals. Oh, that's the dw. F of z times that is equal to, when I put the other thing on the other side, I'm getting minuses of, anyway, this is the Cauchy integral formula. When I put this on the other side, this is minus what I wish I had, but the left is also minus what I wish I had. Check. So that's the proof. That gives me the proof of the Cauchy integral formula, which is part B. I should say, take minus of both sides to get the Cauchy integral formula. So we have a Cauchy integral formula part. And it's a funny in the past we've shown that the Cauchy theorem implies the Cauchy integral formula. But it turns out to be even easier to show that the Cauchy integral formula implies Cauchy theorem. And that's the easy direction. Easier direction. And let's see how that, how would you do that? So the proof of that, suppose you have an f. Suppose f is analytic on omega. Pick an a in omega minus the trace of gamma. And let f of z be equal, capital F of z be z minus a times f of z. So that thing is going to be 0 at a. And then the Cauchy integral formula for f at a, we'd have f of a, which is 0, times the index, which is who cares, equals 1 over 2 pi I integral around gamma, and this time we'd have f of z, which is z minus a times little f of z, And here we'd have z minus a dz. The z minus a's cancel, and we get Cauchy theorem. So 0 is the integral around gamma of f dz. I'm sorry I put an a here, but I meant a z. So that's it. That's a very sneaky, clever proof that wasn't around when I was a student. But it's a pretty nice way to look at it. Any questions about that? I'll have more to say about it after Thanksgiving break. Okay, I got some time now. I can talk about the exam. So let's see, number 1, you were supposed to calculate a real integral involving it was basically this integral here, log of t over t squared plus a squared dt, integral from 0 to infinity. That's what we want. And the hint was, well, take a complex integral around a contour like that. Okay, and we're clear, since we want log of t, natural log of t, we're going to want a complex version of the log, and we have to choose a branch. We want the analytic function we get to be analytic inside and on that contour. So whatever the branch cut is, it shouldn't go into that region. And the most obvious one to take would be the one going down, straight down, from minus pi over 2. And so that's the branch I called log of z be the branch with, that log would be natural log of mod z, that part's always the same, plus I times the argument of z, where the argument is between minus pi over 2 and 3 pi over 2. That way it would be angle 0 here, pi over 2 here, and pi over here. And so that's analytic inside and on. And the reason we had to punch out this little thing is because the thing is not analytic at 0 for sure. So we need to punch that little thing out. Okay, and then so we'll take a log of z over z squared plus a squared. Call that little f of z. It's analytic inside and on that curve. The integral along the right-hand side of the real line is just the integral we want when you parameterize it with z of t equals t. So that's straightforward. The left side, there's different ways to do it. I want my integral to go t from epsilon to r. So I parameterize not L, but minus L. Minus L would start at minus epsilon and go to minus r. So I like to parameterize that by z of t equals minus t, and then t would go from epsilon to r. If you don't do that now, you have to do the change of variables later. I like to do it in the beginning. And then the z prime of t is minus 1. Well, it's the integral along L that I want, so that's minus the integral along minus L, which I now write out. That would be minus the integral from epsilon to r. When I stick minus t in the functions, the minus t squared is t squared. That's nice. And the log of minus t is the natural log of t. So that's nice. And then we have and along that negative real axis, the argument is pi. So it has a plus I pi. So it's not going to cancel. It wouldn't cancel my integral anyway. It's going to be, the minuses are going to make it a plus. So it's actually, the real part is the integral I want. And then there's plus an I times I times some other integral that I don't actually want and I don't care about. The amazing thing is, I don't have to care about it. The real part of the formula I'm going to get is going to spit out my integral that I want. And so I don't even have to calculate that. Many people calculate it because it's an easy arctangent kind of thing, but it's totally irrelevant for us. And then the last steps are to estimate the integral around the outside curve And you just use the... People seem to really like they write out the integral parametrized and then take the modulus and get a real integral dt. That's not, for me, that's not the way to do it. You should use the basic estimate for integrals, which you get, that's how we prove the basic estimate for integrals. So it's like you're proving it every time from scratch if you do that. Anyway, it's more straightforward for me, at least, to use the basic estimate for integrals. The max of f of z on there, let's see, that the length of that curve is pi r. And so the max, you have to be careful. I say underneath there, if you write out the log of r e to the it, it's natural log of r plus it, where t is the argument, when t is between 0 and pi. And that's easy to estimate. That's a numerator estimate, so it's less than or equal to log r plus pi. The biggest that angle could be is pi when you use the triangle inequality. So that'd be less than or equal to log r plus t, and t is less than or equal to pi. And that would be valid when r is bigger than 1 and when t is between 0 and pi. So that's how I got the estimate in the numerator. And the denominator, I have to use a denominator estimate. I need z squared plus a squared to be greater than or equal to something. And when you use the denominator estimate and realize that when r is bigger than a, that modulus would be r squared minus a squared. Okay? So we've done those a million times, and that gives you something that goes to 0. You can use L'Hopital's rule to show that goes to 0. I wasn't very picky about how you showed that went to 0. I was picky about getting a correct, proper estimate there. When you do it for the C epsilon thing, it's all exactly the same. The numerator's estimate would be the same. Oh, but by the way, when epsilon's small, the modulus, the absolute value of log epsilon is important, because log epsilon for small epsilon tends to minus infinity. So you just certainly don't want a minus infinity on the right-hand side. So that's one thing to be careful about. And the other thing to be careful about is the denominator estimate would give you an a squared minus epsilon squared, because epsilon squared minus a squared would be negative. Okay, so that would be valid when epsilon's small, in particular small enough to be less than a and less than 1. So that goes, same kind of L'Hopital's rule thing shows that goes to 0. Epsilon log epsilon goes to 0 from freshman calculus. And so when you put it all together, that would be 2 pi I, integrating around that thing would be 2 pi I times the residue of f. There's only 1 at IA, where the 0 of the denominator is. Okay? And then when you first you let epsilon go to 0, then you let r go to infinity, and you end up with the right-hand side was just I. The left-hand side was I plus I times some integral we don't care about. And we get plus 0, and that would be 2 pi I times the residue. And that residue, the denominator is a simple 0. So it would be f at IA on top divided by the derivative. Let's see, remember we had f over g? When g is a simple 0, it would be f at the pole divided by g prime at the pole. So that's log of AI divided by the derivative of z squared plus a squared is 2z. And at AI, that would be 2ai. That's the easiest way to do it, using that formula for when a simple 0 in the denominator. And let's see, the important thing there is that the log of AI is natural log of A, which is the modulus, plus I times pi over 2. The argument is pi over 2 there. And so you put it all together and you get 2i is the real part of that. And the integral we don't care about is the imaginary. Falls out from the imaginary part. Questions about that? That was a fair amount of work, but it's sort of all work that's somewhat routine, more involved than a typical thing would be on a sitting down exam. In problem number 2, you were supposed to compute this real integral involving a trig function, but the interval is from 0 to 2 pi. And so the examples in class showed you could use complex analysis to do those by writing the cosine of t as e to the it plus e to the minus it, which is 1 over e to the it. And so if we parameterize the unit circle by z of t equals e to the it, cosine of t is a half z of t plus 1 over z of t. And z prime of t is I e to the it, which lucky turns out to be I z of t. So when you plug that into the integral and realize, I need a dz for this to be a complex integral, you multiply and divide by I e to the t. On the top, you get dz. And on the bottom, you realize, that's I z of t. So this is a complex integral in a parametrized form. And there's the complex function inside the integral around c dz. And you multiply that out, and you get a quadratic thing in the denominator. That quadratic thing has 2 roots. One at b plus square root of b squared minus 1, and one at b minus the square root of b squared minus 1. Well, b is bigger than 1 in this problem, and so of course b plus something is even bigger than 1. So the R1 there is outside the unit circle. It turns out R2 is inside. You can see that using very elementary inequalities, the fact that b is bigger than 1. Or you can use the fact that that quadratic thing is z minus root 1 times z minus root 2. So R1 times R2 is 1. And we know R1 is bigger than 1. So that shows you that R2 is between 0 and 1. So if you had to write a proof in 2 seconds, that's how you would do it. Or you'd use just basic inequalities. Which means there's only one pole on the inside. And once again, you would use that simple thing. That's a simple 0 there at that pole, because the derivative of the denominator is 2z minus 2b, which is not 0. That derivative isn't 0 at the pole inside. And so you'd get 2 pi I times the residue. There'd be a coefficient in front, which you pull out, minus 2 over I. The function on top is 1, and then the thing on the bottom has a simple 0. And so when you write it all out, you get what you're supposed to get. Oh, I'm running out of time. Anyway, I'll post these. The key to the third one was the Schwarz lemma thing. And to use the Schwarz lemma, you needed the function to be 0 at 0. And so you'd compose with the Möbius transformation to make that happen. And we know that f of a is equal to 0. And so we need something that sends 0 to a. And the Möbius transformation that does that is z plus a over 1 plus a bar z. And under those conditions, you have the Schwarz lemma at your disposal, and you just do it. Yeah, I'll post these. I don't think I'm going to have time to go all the way through. I'll have to continue this discussion after break, but I'll post these and you can see. The interesting thing about, here's the map. And the last one was a Rouché's theorem. The funny thing, Stein's Rouché's sort of makes it easier to guess what the functions are. I like my Rouchet better. Is time up? Oh, it'll be up in a second. Anyway, Stein's Rouché's makes it sort of obvious what the function